Thank you.
Long time.
I'm sorry.
That's okay.
Yes. So yes, thank you for inviting me back here. Last year's conference was great, and this year's is also well, so far also a great mixture of people from both sides of the aisle. So it's good to sort of cross the aisle and talk to each other. So I'm going to talk about something that I think, I thought it was a good idea to talk about this because it's something that I don't think a lot of people really talk about, namely imaging, right? Because we're interested in, obviously, how do we see things beyond GR? And typically we focus on gravitational waves, which is of course probably the most exciting place to look for these kind of things. But I think it's also a very good exercise to think, black hole imaging experiments, things like the Event Horizon Telescope. What are the possibilities there that we can see? What are sort of the phenomena that we can go look for? And what can we learn again from string theory objects about these phenomena? So what you see here is indeed not a black hole, right? So I am lying a little bit. So I talk about, there's microstructure in my title, but I'm not really going to talk about fuzzballs or microstructure a lot. I'm going to keep it fairly general and try to sort of isolate in black hole imaging the features that we should go looking for, and what black holes or microstructure beyond GR can teach us there. Okay, so okay, good. So I guess I kind of give you the context, right? The context is black hole imaging, the Event Horizon Telescope, right? We've all seen the wonderful pictures. Here's M87. And so they give us a picture of the black hole, right? The picture of the area around the black hole. And so I put picture in quotation marks because, as I'll sort of emphasize along the way, that is exactly not what the Event Horizon Telescope is doing, right? It's not pointing a camera and taking a picture. And that's kind of important when you actually think about, what are observable features. You have to take into account that, you shouldn't be staring at the picture that it's taking, but you should be staring at the actual observations that it does take. And so my question is really, okay, is this a black hole, first of all? And, if it is a black hole, how would this picture be expected to change if there is no horizon, or if maybe the black hole is a little bit different than the Kerr black hole that we're used to, right? That's sort of my overarching question. So a first attempt to answer this question is typically done with some very basic approach. I think Pierre kind of gave a nice introduction to this already. So I'll be quick, right? You basically put your camera here in this nice white point. You're looking at the object which is in the center of some celestial sphere, and you imagine that this celestial sphere, which has a very large radius, right, is emitting light in 4 different colors. And so it illuminates the object in 4 different colors. Giving you something that typically will look, something like this. So you'll see if it's just a black hole, right? Focusing on the guy on the right here. If it's just a black hole, you'll see the flat space limit, let's say, as you move far away from the black hole. So the 4 different colors. And then when you get close, you'll see the curvature effects from which bend the light and give you these Einstein rings or photon rings. And in the middle, of course, if it's a black hole, you'll see the absence of light because some light will just get sucked in and disappear. Now, if you do this for something that doesn't have a horizon, so over here we have 4 different versions of a fuzzball, right? So if something with no horizon, a compact object with no horizon, then in principle, this object should be transparent, right? That's sort of your level 0 approach. That's also what Pierre told us this morning, right? Is that your object should be transparent because anything that you send in should eventually come out, okay? By the definition of not having a horizon. And so indeed, you see that there's now no real black, right? Sort of ignore the little black dots here, but there's no real black features anymore, right? It's all colorful. But of course, this is, again, as was also said this morning, this is something that ignores the important effects that are also present and that affect the light that you're looking at, right? And so in particular, Pierre mentioned the long escape time and the redshift, but also the tidal effects, right? And so not just tidal effects, the normal tidal effects, also the stringy tidal effects that we also heard about from Nick this morning. All of these things will conspire give us something that should effectively be blackened, right? So really these pictures are very misleading because it makes you think, oh, these things are transparent. Whereas really, if you take all of these effects into account correctly, there should be some kind of a darkening factor here, which makes it look effectively black, right? So it mimics this. And then the rings, of course, you already see are mimicked already in this. So this was something that we discussed for fuzzballs in particular a few years ago. And I kind of want to emphasize here that the key feature here, the key property is the compactness of these objects, right? So you can do the same kind of exercise in objects that are not very compact. And so I'm thinking of things like boson stars, which are not very compact, right? And also, if you look at non-compact fuzzballs like this guy, you don't have these kind of tidal effects, right? This kind of tidal effects are not there that you can use to then argue that the light that's sent in experiences something violent and is transformed into part of the microstructure and only emits very redshifted secondary photons. Okay, but so like I said, right, this is sort of this 4-color screen kind of approach isn't really a good approach to actually isolate observable signatures. So what are these observable signatures that we might see, and how do we model them? So I want to argue that there's maybe 2 ingredients, right? There's 2 ingredients that I want to emphasize or focus on. And one is that it's important to be a little bit better about thinking about where the light comes from, right? And how the light is emitted, how the photons are emitted. And so unfortunately, we have very little insight into this, right? We don't really know a lot about the environment of the black hole, except that it's surrounded by some kind of plasma, right? So, but we don't really know where it's exactly located, and is it a thin disk? Is it a thick disk? Is it a fluid or not? These are things that we don't really know. But we can do some approximations. We can do some modeling, and so sort of a very good model, when you compare to experiments, is to treat the matter around the black hole as a fluid. So you do some hydrodynamic simulation, right? You have, of course, charged particles, and there's a strong magnetic field, and of course there's some curvature around. So you need to do some GRMHD, and then you get something which looks like some accretion disk with a jet, right? That's typically what you get out of your simulation. These simulations are very hard to do, very complicated, let's say, very expensive computationally, and so another way of sort of mimicking the same eventual emission that you get is by using some kind of effective models. So this approach was used by these guys, developed a bit by these guys, where here you assume that all the emission comes from some nice thin, optically thin equatorial disk. You give it you give the emission that's coming from this disk some kind of radial profile. So closer to the black hole, there's maybe more intensity, right? And then farther away from the black hole, less intensity, sort of mimicking some kind of a density of charged particles. And then you also give this disk or the fluid, you imagine that it's some kind of fluid, you give it some kind of a velocity, and depending on how you model this velocity, right? Is it infalling? Is it circular? This gives you some kind of a redshift factor that you then factor into your intensity calculations. And then you get something that looks like this, right? It mimics very well the time average of some GRMHD simulation, and also mimics very well what we see, let's say, in quotation marks, at the EHT. Okay, and so the way that you then, or I'll say that in a minute. Okay, so that's about emission. And then the second thing is what I already said, right? We don't really take a picture at the EHT, right? So we don't point our camera and see this. What we do see is, if you imagine taking a cross section of this image, right, then you follow this white line and you sort of see that there's 2 peaks in the brightness, right? So let's say we focus on the blue line here, right? So then you look at the brightness here. So that's sort of a cross-sectional brightness. So what we do see is the Fourier transform of this, right? And that's what's called the complex visibility. And so I'll always focus on the visibility amplitude, which is the absolute value of this complex visibility, the absolute value of this Fourier transform. And so, if you look at it for this red and blue line, it looks something like these red and blue lines. And the actual measured points, the things that the EHT measures, are exactly these dots here, right? These red, blue, there's also some green and black dots right there, right? So those are the things that the EHT measures. And so, so if you want to stare at images and ask yourself, you know, is this an image of a black hole or not? You're kind of missing, you're kind of already missing some information, or said differently, you've had to add some information of your own, right? Because to reconstruct the entire image like this, you kind of need to fill in all of the gaps here in the Fourier transform. And so the only way to do that is to say, I have my nice model, which gives me this, this curve, which then if I reverse the Fourier transform gives me this, this image. So all of this really to say that, you know, maybe the right place to look for, you know, features, what are the features that I can focus on for, let's say beyond GR phenomenology is within the VisAmp, right? Where the actual observations lie. And so, right, and so just to say about this visibility amplitude, so the EHT has baselines in this little square here, but what would be really interesting, right? So this is sort of dreaming about the future, is to be able to go to much higher baselines. So for example, by putting satellites in Earth orbit, we could increase the baseline of our interferometer a lot. And then we could see much more of this visibility amplitude, right? And so what this is going to do is it's going to give us a lot more features to work with. Okay, so how do we, so what do we really want to do then, right? What we really want to do is we want to focus on features in our observations, in our visibility amplitude, that are sort of robust under the things that we don't know. And what we don't know is where the emission comes from, the plasma details. So what we need to do is we need to have a bunch of different kind of emission models, fairly realistic emission models, vary the parameters, let's say, and see what are the features that remain robust under, you know, varying all these things, right? So we need to look for features that are independent of the emission. And well, okay, I'm only showing you one particular visibility amplitude, but it turns out that the photon rings are exactly sort of this. A lot of features of the photon rings, the properties of the photon rings are things that give you very robust features. Okay, so the photon rings, right, in your image are an infinite series of subrings which give you this bright ring always around the black hole, right? So whatever image you've seen, EHT or simulated, you'll always have this nice bright ring around the black hole. And it's very intuitive to understand where these where this ring structure comes from. It comes from the photon sphere, right? So the bound orbits, the bound photon orbits around the object. And in particular, right, these bound orbits are unstable. And so if you imagine that you have some, let's say this is some nice equatorial emission disk, you imagine that you take some emitted photon on this disk, right, which travels on an orbit which is very near one of these bound orbits. Then, you know, for example, you could start with the blue one, and then you travel around one half circle. You pick up another photon before you go out, because you travel through the plane again. Or you could travel on a very nearby geodesic, which is the green one, which travels 2 more times through the equatorial plane before escaping out, right? And so then if you travel along this green line, you'll have more intensity because you've picked up more photons, because you've gone through the equatorial plane more. And so you can continue this game, right? And so the nth photon subring is the one where you've sort of picked up n photons before escaping. And so if you can, you know, really zoom in very high resolution along this, you'll see these n rings typically appear, right? Okay. So these are the photon rings. And so what are sort of some of the properties of this photon ring which are very robust under changing the emission parameters? Well, again, I'm going to focus on how they show up here. One property that's been argued to be very robust is the shape of these photon rings, right? So if you look at it here, it looks like a circle, but more generally, it's something that's more ellipsoidal. And so how does this show up in your Fourier transform signal? Well, basically, the shape, right? The shape is determined by the diameter here. And so the diameter along the cross section of this white line determines for you sort of the wiggling of this visibility amplitude, right? So this is, if I zoom in on this part here, it looks like this. And so this is some sine function which explicitly has this diameter in it. And so if you imagine rotating this white line at different angles around the object, you get the entire shape by extracting from at each angle the diameter. And this is something that has been argued to be very robust across many different kinds of emission. And I should mention, this is something that can be, in principle, measured in some near future experiments, right? So they suggest something where you can put a satellite into Earth orbit, and then you would be able to pick up this shape for the NS2 photon ring. So for one particular photon ring. I'm sorry? Air-based? Earth, sorry, Earth-based. Yeah, no, you need higher baselines. Yeah. So their estimate is that if you put a good enough satellite into Earth orbit, then that gives you exactly the right baseline to resolve the NS2 ring. Yeah. No, not with the current EHC. That's right. Yeah. Yeah. So, but this is feasible, right? You can put a satellite into Earth orbit, cost, I don't know, a few hundred million, maybe something. So feasible. I'm sorry? You need a big what? Yeah. So okay. So good. So it's still so. I'm not an expert. I'm not an expert on this, but what I understand is what they. Yeah, but that's more expensive, right? So what they suggested was some dedicated Earth orbit satellite, which would be at I guess 100 millions, right, to measure the NS2 ring. But then what they're looking at now, as I understand, is to tack on an extra camera to an existing experiment or one that will be launched, which will be much cheaper and which might, because it's a smaller camera, I guess, is not good enough for the NS2 ring, but might resolve the width of the NS1 ring, which for various reasons is okay, but not quite the sweet spot of the NS2 ring. Anyway, this kind of takes us. Yes, exactly. Yeah. So at the moment, we're really only seeing this part, right? The NS0 ring. So that's the shape. The other thing that is something that has also been argued to be very robust is the relative widths of the rings, right? So these subrings each have a width. These widths can differ depending on your emission details, but the relative widths of these rings, which is governed by the Lyapunov exponent, this is something that is very robust. And so if you want to look at the visamp, basically the widths are determined by the lengths here of these segments, right? So you see this segment is very steep, and then there's less steep, and then there's less steep here. But this is something that is very hard to measure, and we don't really think that's very feasible. You know, you can already see here, you know, you don't really see the end even of the NS2 ring, so you need even higher baselines to even be able to see that guy. So this is probably not as feasible experimentally to go out and measure. But I think a very good exercise is to ask ourselves the question, okay, so I know these photon ring shape and the Lyapunov exponent, right, the relative widths. These are things that in principle, at least, give me a robust feature of the geometry, right? And does not depend very much on emission details. So in principle, it's something that we could measure in imaging experiments. So if I change my black hole to be not Kerr, how well does that show up? How well can I really, you know, look at the observations of the shape or the relative widths and say, it is indeed not Kerr. And so that was exactly the question that we asked ourselves in this recent paper. So we took 3 black holes, which I'm not going to go into detail of, but so these are basically 3 different black holes which have a smooth Kerr limit. So Kerr is part of their parameter space, but then you can deviate from Kerr in various ways. And we asked ourselves, you know, for this broad family, right, of black holes, how well do deviations from Kerr show up if you look at these 2 observables? And to be, you know, very brief about the conclusion, this shape, right, which again is this general sort of ellipsoidal shape, is a very universal thing. So this may not be a surprise, or it may be a surprise if you've seen very crazy black holes. But in general, if you really look at the shape of these photon rings, it's very difficult to get something that deviates significantly from the Kerr shape. Okay, so again, I can go into more details if you're interested, but I think as a slogan, that's very clear. The Lyapunov exponent is very sensitive to deviations on the other hand, right? So if your black hole is a little bit different than Kerr, this is something that will show up in the Lyapunov. But again, this is something that is not really feasible to measure. Yes. I'm sorry. What? Yeah, I mean, yeah, okay. So right. So if you allow for an ellipse shape, which is what I'm doing, right? More generally something called a circlipse, but anyway, ellipse shape, then yeah, basically anything that you can think of fits in this, right? And so it doesn't matter if you add charges or even if you add some kind of a multipole bump on the horizon, this doesn't change your shape. Sorry? The black hole, the horizon? Yeah, you can do that. You can squash it. So one, like micronovikos is basically like taking the Kerr black hole and then adding a little squashing in a certain multipole way. It's squashed, but the way that you measure the photon ring, it still gives you an ellipse. So I can say more about this if you want. But yeah. Good. Okay, so what I would like to do is, so this is a little bit maybe disheartening, right? So either the observable, which we can measure, is not really going to see any deviations from Kerr, or the observable that we can't measure is sensitive to deviations. But I want to give you something that, like maybe a hope, right? Something that I think is very exciting, and that we're working on now. So what kind of signatures might there still be, right? So this is again, thank you. This is again my my 4-color screen, just to give you some kind of a reference point. So when you make these plots again, right, these 4-color screens, remember there's this, if you're talking about a black hole, remember there's always this black region in the middle, right? And so we typically call this the shadow. And so the boundary of this shadow is sometimes called the critical curve. And this critical curve is very important also for the photon rings, because you can show that, for Kerr, the photon rings, as you increase n, right? Remember, as you increase the order of these photon rings, they approach better and better the critical curve, right? So the critical curve is somehow, right, the boundary of this black region is somehow the limit of the photon rings as you increase n. And so what you do see though is that when you lose a key feature of the Kerr metric, which is the separability of the nil geodesics, then of course, if you lose separability, you lose integrability. And so by definition, almost you get chaos, right? So something chaotic has to happen. And so you see this in, for example, the fuzzball that I've already shown, right? Null geodesics are not integral, and you see a lot of chaos happening in the middle here in the microstructure. But you also see this in black hole geometries where there's no separability, right? And so just this is just an example of a Manko-Novikov black hole. So again, it looks the horizon doesn't look very spherical anymore. But you see that there's these regions inside where you still have light, right? So there's no well-defined shadow, which is let's say connected and yes, which is connected. Yes. Oh, so like I said, this shadow or critical curve, the boundary of this shadow is where the photon rings approach. And so if my shadow is not some kind of connected curve anymore, then I could expect maybe that my photon rings are not some nice, it's not maybe correct to think of the photon rings themselves as this nice connected curve either, right? And so how might this show up? Well, let me just give you one idea. Yes. Yes, so good. So there's right. So there's many things we can say, right? So here for Manko-Novikov, for example, this is less clear how to interpret it. Here, I would say yes. You interpret this stuff here probably is going to be dark, right? Because the inside should be dark, even though it's chaotic. It should be dark. But nevertheless, right? What might happen is that for fuzzballs, this will depend on the compactness of the fuzzball, et cetera, right? But what might happen is that your photon rings so you might have this photon ring like this, but then when you look very carefully, you might see some kind of a chaotic echo. So I call this a ring echo. I'm not sure if there's a better name for it. In your ring structure, right? So for example, here, this is again the micronovikov, and so you don't really see it here, but if I zoom in, you can kind of see this second echo almost against the first photon ring. And so this kind of structure gives you something that you might be able to see, right? Because this is something that appears in your visibility amplitude. So again, if you, so this is what I kind of said before, right? If you just have the normal photon ring, then the diameter of your photon ring appears in this wiggling of the visibility amplitude, right? And so in particular, the visibility amplitude goes as some square root where there's a sign in there that encodes the diameter. And so if you now include this ring echo, let's say, which is this guy over here, right, which is even too faint to see, then you'll get something that looks like a well, there's three peaks, so the Fourier transform of this is not going to be a simple sine. You have the sine, and then you have interfering signals here, right? So you get some kind of a beat signal here when you look at this visibility amplitude. So that could be something that you could actually pick up, right? Again, this will depend on how faint this is and what the distance is, of course, between the primary ring and this ring echo as well. And all of these things will depend on your specific model, right? Whether you're thinking of some deviating black hole or whether you're thinking of some fuzzball and how compact this fuzzball is, et cetera. But this is at least maybe a first indication of some signature that one could focus on when you have a given model in mind. Okay, so the last thing I want to say, I know I'm running out of time, right? So So this is just my last slide before I conclude. It's sort of a tangent. I forget who said this yesterday, but or even before. But you know, how do I ask these questions, right? You need to be able to consider different objects, consider different metrics. I need to have different emission models. I need to be able to simulate my experiments for different objects, right? So I need to develop tools that can do this for me and can do this easily for me. And so this is exactly sort of the reasoning behind this ray tracer that we've been working on for a few months now, where we really want to, make it very easy for, you have a nice four-dimensional object with some metric. Okay, you put it in the ray tracer. It's very easy to implement the metric, and then you can do a variety of emission models and get the visibility amplitude directly out of it, right? And extract the signatures. And I think this is, well, first of all, it's an open invitation if you have more metrics that you would like to plug in. But I think this is an important step for our community, the Beyond GR community, let's say, is to really think about how can we build such tools for phenomenology, right? Because I think it was Vitor who said this, right? We need to be able to simulate the observations for our objects, to make contact with this world. Okay, so that's what I've been telling you about. I hope you take away that for black hole imaging, you need it's important to focus on the right things, right? If you really want to make contact with observations. And so in particular, think about emission and think about the actual observed visibility amplitude. And so then I talked a little bit about photon rings, right? And so I think maybe one exciting thing is these ring echoes that you might see as a signature of chaos, of breaking down, of separability, of null geodesics in your images. Okay, I'll stop there. Thanks.
Yeah, sorry. Okay, so we have also a discussion session. So questions for the speaker or for other speakers?
Yes, a comment, please, more for the discussion, but very much related to that. So I see a bit sort of dichotomy in the sense that on the one hand, there is this great effort in trying to be very accurate and as much precise as possible in computable observables, be they like shadows or rings or ring down or echoes or whatever, multiple moments, everything, on specific, say, microstate solutions. On the other hand, there was a Nick's attitude yesterday and the other day saying, well, I mean, within the model, everything washed out, we should get just a black hole. This is just a single microstate, so it's a coherent, so on and so forth. As a phenomenologist, I mean, I tend to like this approach of go out and try to model and observe and constrain. But on the other hand, because time is finite, we want to do something that eventually the community thinks is valuable and useful. So the question, I guess, is for everyone is, should we actually go in this direction and take specific solutions and understand their phenomenology very carefully, or is it a waste of time? Because anyway, even if, suppose that you find a smoking gun deviation, in a few years from now, people will say, okay, I mean, this is not what the fuzzball model would predict, because it's you are doing something very specific, but on a model that is not realistic. So yeah, it's an open question, I guess. What is your take on this?
Well, I have some thoughts if I can react. I guess I can react because I have a microphone on.
A question of a question.
No, I think it's a valid, yeah, there's some tension, right? Because what you can do is typically you have one given object and you can do something with that object. But then what you want to do is you want to have some kind of a generic prediction for, okay, I expect, something like this to happen, but that's not what you do when you look at one object, right? So I think for me, using fuzzballs, it's really a matter of using them as tools, as toy models, to understand where the interesting features might lie, right? And so I think when I'm thinking of things like black hole imaging, then I typically have in mind, okay, fuzzballs are good compact objects, right? And so if I want to understand, what might be visible signatures of compact objects, I can look at fuzzballs and plug them in my ray tracer and then get some insight there. But of course, if you think about but I don't take them seriously as a quantum state for a black hole in that case, because then, like you said, you expect that, okay, the object is in equilibrium, and so it's going to be in a typical state. There should not be any measurable difference with the black hole. So then I'm not even then I'm not going to learn anything by that kind of approach. But so maybe a good thing as an example, right? So this was something that also came up yesterday, I think, right? And also today when Josef was talking, right? We learned something from studying fuzzballs, namely, maybe in the merger process, there's going to be something that happens which releases energy into a channel that we weren't thinking of before. And so this is what I just said is a very generic thing, right? And so that's something that we can go look for without tying ourselves to any particular fuzzball model. We can ask ourselves, okay, look at a bunch of merger signals. Is there some kind of energy loss that is statistically significant and isn't predicted by GR? But
yeah, so I have a comment and a question. I guess the comment is that even though the shape is universal, the size of your critical curve depends on the geometry. So
yes.
If you have a means, which we have for Sagittarius A, for example, of measuring the gravitational mass with the motion of faraway objects, then you have a means of testing whether or not it's a curved black hole by comparing sizes, for example.
So
even though the shape is universal.
Yeah, can I just react? So
no, of course,
so I agree. I completely agree. If you have a second means of doing determining what your shape should be, then of course this gives you a test. Although what is typically true is that your shape is very degenerate, right? So if you know your mass and angular momentum, that's good, but then typically you can still kind of wiggle around in
those are
anyway,
intrinsic
yes.
limits. And the comment, I guess, is related to what you said about the inner structure being dark. I would like to understand that, because the argument that's made relative to Sagittarius A and also M87 to some extent is more or less independent of what you have in the center. So these objects have been there for millions of years. So they should have gotten into thermodynamical equilibrium with the
Yes.
environment, right? So even if the material is highly absorbing, after millions of years, it should be giving away what it's secreting. So I think we should be careful with the argument that fuzzballs or whatever else should be dark in the inner circle.
I'm not sure I completely understand what you mean, right? Because it could be in thermal equilibrium depends on your time scale, of course, but I think also what is true is let's say we take some Kerr black hole now, right? Let's Sagittarius A, and we give it some accretion disk. There's going to be stuff falling in all the time, and so what you're saying is at this point it should be in. If it's not a black hole, it should be in equilibrium. The stuff that falls in is coming out. Right, but then I would say, you know, the escape times that you could have could be very, very large, right? Yes, indeed, yeah. That's what I would.
Further questions, observations, thoughts, hopes? Okay, so let's thank the speakers.
Joseph had a.
The joke about the accident. Go ahead with the joke. Yeah, the man.
No, it's about, calling it F-O-O-R-T. So, sounds like a Flemish thing with like a port, like a long Flemish thing.